solving linear systems of equations is our big tool for the semester. And today is the day that we first get that exposure of what are the different techniques that we have to do that. So really there are three that we're going to focus on today. And the three are, first of all, graphing. And that's part of what this app is going to help us to really to grapple with here for a minute. And the second and third are the more algebraic techniques. The technique of substitution and the technique of elimination. And the funny thing is that even though these three techniques kind of play a central role when you first learn about systems of linear equations in algebra, so standard algebra, algebra 1, algebra 2, whatever, we end up doing them in this course in a different way once we've built up a little bit more superstructure around the ideas of the course. Namely, once we've built up the idea of a vector and the idea of a matrix. And that process of building begins with tomorrow's class, where we're going to start looking at linear systems of equations as having a vector identity to them. But for today, when we're not dealing with vectors and we're just dealing with the equations themselves, these are our three techniques. So just to introduce you to how this little applet works, what the applet does for you is it visualizes the system of two linear equations, which is a times x plus b times y, where x and y are the variables we're trying to solve for, equals c, and d times x plus e times y is equal to f. So this is what we call a system of two linear equations and two unknowns. So our two unknowns are x and y. And so those are the variables whose quantities we want to solve for. And so a solution of this linear system of equations is a value for x and a value for y. And then the rest are what we would call the coefficients of the linear equation. Coefficients, a, b, c, and d. Actually, let's say this. Let's call the coefficients a, b, d, and e. So these constants over here on the left-hand side of the equation that define what belongs on the left-hand sides. And then we also have what we might call let's call them the targets. And that language is a little weird for now, but we'll see tomorrow why calling them targets might be a natural thing to do. And so those form the right-hand sides of these equations. So really a 2-by-2 system of linear equations is characterized by these 6 different quantities, the 4 coefficients on the left-hand side and the 2 targets on the right-hand side. And what the applet in front of you permits you to do is to take those quantities, a, b, c, d, e, and f, and just give them different values by adjusting the sliders that are on here. And as you learn from your Algebra 1 course, I suppose, each one of these equations describes in the xy plane a straight line, which, not coincidentally, is where we get the term linear from in linear system and linear algebra, that these are the kinds of objects that we're primarily going to be working with. So, for instance, the initial setup of this app has 2 equations in it. The first one, x plus y equals 2, and its graph would be this downward sloping line, right? If we solve that for y, it's y equals 2 minus x, and so slope -1, y-intercept positive 2 is the blue line sloping downward. And then likewise, the second equation that's shown here, x minus y equals 2, describes the second line, x minus y equals 2. And so now here's my question. What does it look like to have a solution? Where do we find the solution of this 2-by-2 system of equations on this picture? We're looking for a value of x and a value for y, which satisfy both equations at the same time. Where do we find such an x and y on this graph? It would be a point that it has to lie on the first line. In other words, x plus y has to equal 2. But it also has to lie on the second line, because x minus y has to equal 2. Therefore, if it has to lie on both equations, it has to lie on both lines, and therefore it must be a point of intersection. Intersection of the two lines. So, in this example, we would find our solution right there.
Is there a way to see what...
Oh, is it still doing that? No wonder. Yeah, I know there's a way, it's just this is really stubborn for some reason. Some projectors do this to me and some don't. Oh, there we go.
Just again, you can like throw something at me if I have to go forward, but can we think for each equation the line represents kind of the like solution space
Sure.
for x and y, and
Right.
then this is the intersection of both of those solution spaces.
Mhm.
So the solution for the two different.
Right. Each one of these equations gives us one line. And so when we put both of those equations together, we're finding what both of those lines have in common. And in the sense that each of those lines is a solution set, well, yeah, it's the solution set of the equation x plus y equals 2, and then x minus y equals 2, and then we're putting those two together to find what they have in common. So the method of solution by graphing is just this, right? You graph both of those lines and find where their intersection point is.
Intersection in like a set theoretic way,
Mhm.
not just.
Yes, it is also that. Yep, it's the intersection of the set of points defined by the equation x plus y equals 2 with the set of points defined by x minus y equals 2. And so we find that this, how many solutions does this system of equations have? In other words, at how many points does this pair of lines intersect? 1. That's an important observation, by the way, and it's one that when we get into groups today, I'm going to ask you to kind of play around with a little bit. Because it's almost, when we're looking at it in a graphical sense, it's almost a geometry question. In how many points may a pair of lines intersect? Well, 1 in this case. Well, right, what are the other options is going to be something you look at in your groups today. Okay, so that gives us a visual way to understand what the solution of this system of equations is. But if we want to be specific, we could find the coordinates of this point of intersection and write down what the coordinates are, and we could sort of, estimate it from looking at the graph. But, estimation is for applied mathematicians. Let's try to be as precise about it as possible. Let's look at the algebraic methods of solution, the two different ones. So substitution on the one hand, and elimination on the other hand. So let me copy down this system of equations. So x plus y equals 2, and x minus y equals 2. So how do you think the method of substitution works? If you're familiar with solving linear systems by substitution, what do you do first?
You solve for x or y and then put it into the other equation?
Right. So you take one of the equations and you rearrange it to solve it for one or the other of the variables, and it doesn't really matter which. So which one would we like to solve for? Just pick one.
The first one, y equals 2 minus x.
Sure. So if we solve the first equation for y, we get y equals 2 minus x. And then once we have that solution, now we know explicitly how y relates to x. We can substitute that expression for y into the second equation, being careful to make it a quantity here, and then solve the result. So x minus the quantity 2 minus x is equal to 2. Now we've reduced the number of variables in our equation by 1. So now we're down to a single variable, and we know how to solve a single variable linear equation. Let's just simplify the left-hand side. X minus x is going to give me a 2x minus 2 equals 2, from which we get 2x equals 4, and hence x equals 2. But we're not done, because every solution of a linear system of equations has both an x and a y. A 2 by 2 linear system has an x and a y in it. So now that I know that x is equal to 2, how do I find y? Plug it in to what?
The first equation.
The first equation. Or the second equation. Or any of the equations we got along the way, right? Because they all should be telling us the same thing. Let's just, for the sake of easy, let's plug it into this equation which we have that explicitly relates y to x. If y is equal to 2 minus x, then since x is equal to 2, y is equal to 2 minus 2. So, all told, we get a solution of our linear system of equations that looks like x comma y equals x is equal to 2 and y is equal to 0. So xy is equal to 2, 0. And sure enough, that jives with the picture that we had when we graphed this pair of equations. This point indeed looks like it's on the x-axis, and so the y-coordinate is 0. And if we try to, as carefully as possible, measure the x-coordinate, we do find out that it certainly looks like the x-coordinate of that point should be 2. So there's some justice in the world here, that our picture matches up with our algebra, and that's the method of substitution. Right? We solve for one of the variables explicitly, then we plug in that value to the other equation, and now that equation has only one variable, and we can solve it, and back substitute to get the value for the other. Questions so far?
One thing you could also do is substitute what 2 is. So you can express x plus y as being equal to x minus y, cancel the x's.
It's a little sly, but we could. I mean, and it's certainly not going to be that easy always.
Yeah, of course.
But yeah, sure.
I'm relying on, the only number that's negative, well, that's equal to is added and inverses.
Right. So let's talk elimination. As it turns out, I think this will be borne out over the semester, but I think elimination is really the method that we end up sticking with on a permanent basis. For no particular reason. I think substitution tends to introduce, in general, a lot of messiness into the problem. In particular, if I have a coefficient on y, then we end up having to divide by that coefficient, and so we get fractions popping up everywhere. Elimination is kind of a way of getting around that as much as we can. And instead of having to take a single equation and turn it on its head, what elimination lets us do is take the equations together and have them kind of all sing in harmony, if you will. So if you're familiar with the method of elimination, how does it work?
Subtract one equation or from the other.
Right. What's the goal, by the way? How do I know whether to add or subtract or what to do when we're solving
Eliminate a
elimination?
variable.
Right. The goal, as always, is to reduce from 2 variables down to 1 variable, because as soon as we're down to 1 variable, we can solve. Right? And it's a process of adding, or possibly subtracting, one equation to another. Add or subtract equations together. So in our example, what can I do to these 2 equations in order to eliminate a variable? Should I add or should I subtract? Let's try adding. If I add these 2 equations together, what am I eliminating? I'm going to eliminate y, because here the coefficients of y are equal and opposite. So if my goal is to eliminate y, I should add these 2 equations together. And when I do, the right-hand side becomes 4. The left-hand side, the y's have vanished, but the x's have added together to give me 2x. That's pretty. Right? Now it's a single variable equation, and I only have one step to do to solve it. Divide both sides by 2. And as soon as I have that value for x, now how do I get my value for y?
Just minus them. So,
Oh, sure. No, absolutely. Let's do that. I kind of like that. We could have, if our goal was to eliminate y instead of eliminating x, we could have subtracted these 2 equations instead. So let's get that in here too. X minus y equals 2. And if I then subtract, and when you subtract, remember, always be careful that you're subtracting the whole quantity. So that on the left-hand side, 2 minus 2 becomes 0. On the right-hand side, x minus x goes away. But y minus negative y becomes y plus y, 2y. Now I have a single equation that tells me the value for y. Just dividing by 2, y is equal to 0. So again, same answer, and it better be the same answer, because this is still the same system of linear equations, just done with the process of elimination instead of substitution. By the way, what is another way that once we know x is equal to 2, how else could we have gotten to that value for y without going back to the beginning? Plug it in. Exactly. That's always an option. Plug it into either equation you like. Let's say I plugged it into the first, and I would have had 2 plus y equals 2. Subtracting 2 from both sides gives me the value of y. So either way, you can either go back to the beginning and eliminate the other variable, if you like, or since we know the value of x, we can use that information to make our process a little quicker and just substitute that into either one of the equations that we started with. But however you slice it, the solution of this particular linear system of equations is right there, 2, 0. And that's looking at it from 3 different ways. We can graph these 2 lines and look at their intersection point. We can substitute, so solve for one of the variables in terms of the other and plug that expression into the second equation and solve. Or elimination, where we target one of the variables and say, let's either add or subtract or whatever we have to do to these 2 equations to make that variable go away. And that gets the whole process started. Questions on any of these methods yet?